Welcome back. In this video, I'm going to talk about the Gateau derivative in details, and I will give you a practical methodology to find the Frechet derivative or study the Frechet differentiation at a point. So the Gateau derivative is another way to extend the notion of derivative, and it's an extension actually of the notion of directional derivative that you probably encountered in calculus. Okay, so let us revisit first this notion. If you have a function of several variables defined on an open set as usual, and we consider a point A and a vector V in Rn, the directional derivative of f at A along the vector V, when it exists, is this limit. Okay, here t is a real number, so we can always divide by t. So limit of A plus tv minus f of A over t. So of course it depends on A and V. Okay, when it exists, we use one of these symbols, nabla v f of A, nabla sub v, or del f over del v at A, or f v prime at A. And you may also encounter other symbols. Okay, and observe that this can be written as a derivative at 0. So if we consider the function of t, we fix everything and we consider this function f of A plus tv, then at 0 we have f of A. So this is just f of A tv. If you call this phi, then this is just phi of t minus phi of 0 over t minus 0. So this ratio, by definition, if it exists, is the derivative at t equals 0 of this function. Okay, and it's easy to prove that if f is Frechet differentiable at A according to our definition, then f has a directional derivative at A along any vector v, and the directional derivative along v is given by just the dot product between the gradient and the vector v. Okay, so it's a real number. This is very easy because the Frechet differentiability at A, if you just replace h in the definition by tv, v is fixed here, but t varies. So replace h by t, or sorry, yeah, tv or tu doesn't matter. So here it should be tv actually, not tu. So actually, the name of the vector can be anything. Could be u, could be v, could be n, could be h. Doesn't matter. Okay. So here I used v, so I fixed v. So if you replace h in the condition of Frechet differentiability, you'll get f of A plus tv minus f of A minus or equal the Frechet derivative at h. But since it's linear, I can put the t outside, plus a small o of h. But a small o of h is a small o of t because u is fixed. Okay, so we get this condition. Okay, this is a consequence of the Frechet differentiability at A. And if you don't like this, you can use the usual epsilon delta. Or so when we divide by t, we get that this ratio is just the Frechet derivative at v plus small o of t over t. And when t tends to 0, so this is a constant, and this tends to 0. So we see that this ratio has a limit, and the limit is the Frechet derivative at A along v. And therefore, and as you know, we know that this is just the gradient of f, the dot product between the gradient of f at A and v. Okay, so Frechet differentiability implies the existence of a directional derivative along any vector, and the directional derivative is just the inner product or the dot product between the gradient and v. Okay. Now, this relation between the directional derivative and the gradient can also be obtained by the chain rule, because the directional derivative is just a derivative. So it's a derivative of a composite map. And the chain rule tells me how to do that. We didn't learn that yet, but as you may expect, the derivative of two composed map, it's the derivative of f at the point times the derivative of what is inside. Or evaluated at the what is inside. But the derivative with respect to t of what is inside is just v. Okay, so this is the chain rule. So I obtain again that the direction derivative along v is just the Frechet derivative, or which is actually a gradient, if you like. Same thing. Now, you also have to observe that if f has a direction derivative at a along any vector, then it has partial derivatives at a. This is very straightforward, because if you take v to be any element of the canonical basis E1, En, then the existence of the limit, if you go back to the definition, if this limit exists for v equal ei, then this precisely means that the partial derivative with respect to the ith variable exists. Okay. Now, this relation, so let's remark before we move to the Gateau, the more general concept of Gateau differential. This important relation giving the direction derivative as the inner product of the gradient with the vector has a very important consequence. Okay. To fix the idea, suppose that the length of the vector, or the norm of the vector, is fixed. Take it 1. Okay. But v can vary. Okay, so we have here v varies, and let theta denote the angle between the gradient of f at a and this variable vector v. Now, therefore, we can write this direction derivative as the norm of the gradient times the cosine of the angle between the gradient and v. Okay. Now, what is the interpretation, the physical or geometric interpretation of this direction derivative? It's the limit of a ratio. Therefore, it is a rate of change. It is an instantaneous or a pointwise rate of change. So the direction derivative, by definition, is the rate of change, pointwise, should not say instantaneous, but it's the rate of change of f along at the point A. So it tells me how much does f change when it is at A. So when is this rate of change biggest? I fix everything here. So A is fixed, but V varies. Okay? But V has a norm 1. So when is this quantity maximum? This is a constant here. So the cosine can vary. What is the maximum value of cosine? It's 1. And this happens when theta equals 0 or a multiple of 2 pi. So this means that the maximum of this rate of change happens when V and the gradient are parallel. So they point in the same direction. Okay? And therefore, we can say that the gradient of f at A represents the direction in which f increases the most. It's a very important and useful interpretation of the gradient. Okay? Because you know that the gradient is just the vector of partial derivatives. But why is it so important? It's important because it tells me in which direction f increases the most. And therefore, minus the gradient represents the direction in which f decreases the most. And this has a very important consequence. This idea that minus the gradient represents the direction in which f decreases the most is the central idea in all minimization algorithms in machine learning, okay, and sometimes in numerical analysis. So, in a minimization algorithm, we search for a minimum, hopefully a global minimum of a function of several variables. So we start with a certain initial condition, and we iterate. So we define a sequence. So all these schemes actually are something of this form. So we start with x0, and then we iterate. We subtract from the previous step a multiple of the gradient. So what does this mean? It means that at each step, we move toward the minimum because we move in a direction opposite to the gradient. So in the direction that leads to a biggest decrease of the function. Now you may say, so this is one of the simplest scheme actually, and in machine learning, this constant alpha is known as the learning rate. Okay. Now these algorithms do not always converge, and this is why it's not an easy problem actually. But when it converges very fast. Okay. So this concludes what I wanted to say about the directional derivative. Okay, now we move to the more general case. So we consider a function defined on an open subset of a norm space and taking value in another norm space and same setting. And the Gateau derivative of f at a along the vector v, when it exists, is the same limit. So here we are dividing by a real number. We're not dividing by a vector. And we use usually one of these symbols, df at av or d sub vfa, and you may encounter other symbols as well. We'll use this for simplicity. So we will use small d for the Gateau derivative and capital D for Frechet derivative. So in order to minimize confusion. And once again, the Gateau derivative is the derivative of this map when t equals 0. Okay, so as we expect, when f is Frechet differentiable at a point, then, I should say Gateau differentiable. So Frechet differentiability at a point implies Gateau differentiability at that point, and they are the same. Okay, so just same proof, okay, as the previous proposition. However, the converse is not true. Okay. So first of all, the map, the Gateau derivative, need not be linear or continuous in V. First of all, it need not exist. But if it exists, it's not necessarily linear or continuous, unlike the Frechet derivative, which is by definition linear and continuous in the argument, in the increment V or H. Okay, now some mathematicians include in their definition of Gateau derivative the linearity and continuity of this map. But even if this map is linear and continuous, it doesn't mean that f is Frechet differentiable. Now I'll give some very important counterexamples. Okay, so first example where the Gateau derivative exists but is not linear. Okay, take simply the function of two variables, x, y, given by x cubed over x squared plus y squared if away from the origin and 0 at the origin. And so once again, if x equals 0, this is 0. If y equals 0, this is just x. Okay, now if you go back to the definition, okay, so you compute, you take an increment uv, or you can call it u1, u2, or v1, v2, or h1, h2, or hk, as you like. It's not important. So here you take a equals 0, 0, and v, let us say, equal uv, just two components here. So if you do the increment, so you'll get tu cubed, tu to the cube over tu squared plus tv squared. So when you simplify and divide by t, you will get this function. So if the increment is 0, of course, it's always 0. By the way, df at a0 is always 0, okay, by definition, because, okay, if you go back to the definition, when you put v equals 0, you just get 0. Okay, so this is not interesting. So the Gateau derivative along the increment 0 is 0. Okay. Now, so you just have to see what happens when uv is different from 0, 0. And in this case, when you simplify, you will get, when you simplify by t, so you get t cubed here and t squared here. And then when you divide once again by t, you will get this constant, and therefore the limit is this. And now this is far from being a linear function in the couple uv. Okay, of course it's continuous but not linear. So this is the first counterexample. So we conclude that here this function is continuous and has a Gateau derivative at 0. But the only problem is at 0 actually, because at every point different from 0, the function is as smooth as you wish. So it's Frechet differentiable. It's C1 actually away from 0. Okay, but the only problem is at 0. So in particular here in this example, we conclude that f is not Frechet differentiable at 0. Now, an example where the Gateau derivative exists is linear but not continuous is this one. Consider an infinite dimensional norm space. We shall prove next year. I don't know if you proved this before, but on any infinite dimensional norm space, we can find linear discontinuous maps from E to R. Okay. So I will ask you to, if you don't know that, just assume it. I will prove it next year. So, and this is actually one of the big differences between finite dimensional and infinite dimensional norm space. So as you know, continuity on an infinite dimensional norm space is automatic. Okay, so when you work with an R2 or Rn, you don't need to check continuity of a linear map. Okay, it's automatically continuous. But it becomes less trivial when the space is infinite dimensional. So if you take f to be linear but not continuous, and you go back to the definition, you'll see that the Gateau derivative at x along any vector v is just f of v. So it's constant in x. So it's linear actually in v, but it's discontinuous. So this is an example where the Frechet derivative, the Gateau derivative is linear but discontinuous. So we conclude that f is not Frechet differentiable, but it's Gateau differentiable everywhere. Okay. Last example where the Gateau derivative exists is linear and continuous, but the Frechet derivative still does not exist. Okay, this is the example. Function of two variables. F of xy equal x cubed y over x6 plus y squared away from 0, and at 0 it's 0. Okay. Here, if you go back to the definition and you compute f of 0, 0, 0, th, tk, or tu, tv, as you like, you will find after simplification here you get t4 because t cubed times t, and here you factor by t squared, and then you divide by t. So after simplifying, you get t, and this tends to 0 actually, as t tends to 0, no matter what is xy. Of course, if one of them is 0, then there's nothing to prove actually. So we see here that the Gateau derivative at 0 is the identically 0 map. So of course it's linear and continuous. But observe that here, if you use polar coordinates or anything you like, actually, you will see that f is not even continuous at 0. Okay? Just use polar coordinates. Or if you like, if you take, for example, you may take, for example, the limit when x equal y along the first bisector, what happens, and for example, you can see what is the limit along the curve y equal x cubed, for example, what happens, or x equal y cubed. So you get different limits, and therefore f has no limit at 0. Okay, so it's not continuous there. So this is the last example. So this is, I think we clarified the connections between Gateau derivative and Frechet derivative. And now, after all this exposition, we can come up with a methodology which may help you solve the exercise. Because in the exercise, you are asked to study the Frechet differentiability of a given map. So we proceed as follows. So first of all, we see if f is continuous at the point under consideration. So if it's not continuous, then of course it cannot be Frechet differentiable at that point, because unlike Gateau, so Frechet differentiability at a point implies continuity at that point, but it's not true for Gateau differentiability. So discontinuity at the point rules out the existence of a Frechet derivative or differential. Now, otherwise, we study this limit. Okay. Now, if this limit does not exist, then we conclude that the function is not Frechet differentiable at the point. If it exists but is either not linear or not continuous, then we also conclude that the Frechet derivative does not exist. Now, if the limit exists and is linear and continuous in the argument v, you may call it h, anything you like actually, then this Gateau derivative is the unique candidate for the position of Frechet derivative, because if the Frechet derivative exists, then it must be that limit, as by the previous proposition. So we have to see whether we can approximate. This could be a linear approximation of f, as in the definition of it, or not. If this identity holds, then we conclude that f is Frechet differentiable at a, and the Frechet derivative is just the Gateau derivative given by step 2. But if you find that this relation does not hold, then you must conclude that f is not Frechet differentiable at a. Okay, so here you have it. So this is a kind of algorithm which may help you in finding the Frechet derivative. So this is actually a method of research, if you like. So because you may ask, okay, well, I understood the definition of Frechet derivative, but how do I find it? Okay, here it's a way. So just it's easier to find in general the Gateau derivative because it's a limit. And then you proceed as we said. So this concludes this video. And thank you for your attention and see you next time.